The lesson outcome for this video is, I can graph exponential growth. Well, before we actually talk about exponential growth, I'm first going to remind you how we graphed linear functions in a previous unit. So remember that a table can always be used, a table of values. Typically, I'd write my table of values like this, x and y, and we'd fill in some numbers here for x, plug that x value into our equation, and then get our output for y. And then those are all x, y coordinate pairs that we can plot on our graph. So we're going to do the same thing using this table shown. That helps us just set up our work. So first of all, we're going to go ahead and put this x value, -2, in for x in our equation. So y equals 3 times -2 plus 2. So we just have to make sure to follow the order of operations. 3 times -2 is -6, and -6 plus 2 is, -4. We'll go ahead and do the same thing for this table all the way through. We're going to put a -1 in this time for x. 3 times -1 is -3, plus 2 is -1. When we put a 0 in for x, we get 3 times 0, which is 0, plus 2, which is 2. If we put a 1 in for x, 3 times 1 is 3, plus 2 is 5. And lastly, if we put a 2 in, 3 times 2 is 6, plus 2 is 8. Again, each of the xy coordinate pairs that we're going to plot in the graph are found by looking at this x coordinate that correlates with this output. Input, output. So -2, -4. And then we had -1, -1, 0, 2, 1, 5, and 2, 8. So when we graph each of these, we're going to find -2, -4 on the coordinate plane, which is right there. And then -1, -1 here. 0, 2, which is here. 1, 5, which is there. And 2, 8, which is there. And we see that each of those points is in a line because this is a linear function, and we graph the line through those points. So there's really nothing very different about this next example, except for now, instead of having a linear situation like y equals 2x plus 3, we have 2 times 3 raised to the x power. And that's what makes this an exponential situation, is that the variable x is the exponent. So we're going to go ahead and do the same thing, but things are going to be a little different when it comes especially to our negative exponents. So to kind of avoid that confusion at the beginning with these negative values for x, I'm actually going to start with 0 right here, go down, and then we'll come back to this one. So the first thing we're going to do is put a 0 in for x. So y, let me change my thickness of my pen, y equals 2 times 3 raised to the 0 power. Now again, following the order of operations, we need to do the exponent before we multiply. So be careful of that. We don't do 2 times 3 is 6 raised to the 0. We do 3 to the 0 and then do 2 times that number. So 3 to the 0, remember from our exponent rules unit, 3 to the 0 power is 1. Any number raised to the 0 power is 1. So that'll be 1. So this will be 2 times 1, and 2 times 1 is 2. We'll go ahead and put a 1 in for x, so 2 times 3 to the first power. Again, our exponent first, 3 to the first power is 3, and 2 times 3 is 6. And then we've got y equals 2 times 3 to the second power. Be careful right here, 3 to the second power is 3 times itself twice, so 3 times 3, which is 9, and we have then 2 times 9. 2 times 9 is 18. That will not fit on this coordinate plane to the right, but we'll make it work out anyways. All right, now backing up a little bit, we need to now raise this 3 here to a couple other x-coordinates, and they are negative x-coordinates. So when we do this, it might seem a little confusing at first, but I think you will catch on just fine. So y equals 2 times 3 raised to the negative 2. So we worked with negative exponents again in a previous unit, and we get 3 to the negative 2. If you remember, if you have a negative exponent, the way I taught it was that we're going to turn this into a fraction, and we're going to think anything with a negative exponent, we're going to move to the denominator, or to the other side of the fraction, I should say, and make the power positive. So now we have 1 over 3 to the second power, which is 1 over 9. So 1/9. So what we have right here then is 2 times 1/9, which is technically 2/9. Now you might not want to try to graph 2/9. The other thing you can do is you can type this right here into your calculator. And the way you do that is you would type 2, and then the times sign on your calculator is probably the x, even though that's saved for a variable these days in algebra. But 2 times 3 raised to the negative 2. So look for this little up arrow looking thing. That is called a caret, and it helps us raise things to different powers. So when we do that, we're going to go ahead and get 0.2 repeating, 0.222. So that will be what we get here, 0.222. All right, and we're going to go ahead and do this last one in here. Y equals 2 times 3 raised to the negative 1. Again, if you use your calculator to go ahead and compute that, that's fine. Or if you think about 3 to the negative 1 would be brought to the denominator. So you're going to get 2 times 1/3, which is 2/3, which is 0.66 repeating, so 667. All right, so once again we have our coordinates, negative 2, 0.222, negative 1, 0.667, 0, 2, 1, 6, and 2, 18. And we're going to go ahead and plot those points on our coordinate plane. So negative 2, comma 0.222, so that's just slightly above the x-axis right there. And then we've got negative 1.667, so 0.667 is about 2/3 of the way towards 1, so maybe right about there. 0, comma 2, which would be here. Oops, sorry about that, right there. 1, 6, just about, that's not 6, that's 7. Let's erase that and get the correct point in there, which would be right there. And 218. Now 218 would be off the graph, maybe more like up here somewhere. Because if this is 10 right here, we need to go up 8 more. So that's probably about right. Now you'll notice that this is not linear. This is not the graph of a line. What this is, it's a graph of an exponential function. So it follows a curving path like that. It starts off as at a slower rate of growth, and then it grows exponentially quickly. Okay, so let's go ahead and try one more exponential graph of exponential growth. And we're going to start with y equals 1/2. Let me get my pen to work a little better for me. So y equals 1/2 times 2 to the negative 2 power. Again, if you use your calculator, you can multiply 0.5 times 2 raised to the negative 2, and that is 0.125, so 0.125, that's a 0, if you can believe it, okay? And then we'll go ahead and do y equals 1/2 times 2 to the negative 1, and when you do that, you're going to get 0.25. At this point, why don't you go ahead, pause the video, see if you can fill in the rest of that chart, graph your points, and then check back to see how you did. Okay, so we're going to have y equals 1/2, hard to squeeze that in there, times 2 raised to the 0 power. Anything raised to the 0 power is the number 1. So what we have here is 1/2 times 1, which is a half. The next one is y equals 1/2 times 2 raised to the first power. Well, 2 to the first power is 2, and then 1/2 of 2 is 1. And lastly, we have y equals 1/2 times 2 raised to the second power. 2 to the second power is 4, 1/2 of 4 is 2. So the points that we are going to plot are -2, 0.125, -1, 0.25, 0, 0.5, 1, 1, and 2, 2. We'll go ahead and plot those points. -2, 0.125 is really close to that x-axis right there. -1, 0.25, we move that up just a little bit, maybe not quite to there. 0.5, which is going to be about half the distance between 0 and 1, right? And then we've got 1, 1. It's kind of hard to get these points on this graph. Sorry about that. And 2, 2. Now it's hard to see the graph at this point looking at what type of curve this might turn into. So let's go ahead and actually find one more point to help our graph kind of look a little bit clearer. All right, so what we're going to do is we're going to go ahead and put 3 in for x. Now if we do that right here, 2 to the third power is 2 times 2 times 2, which is 8. So we're going to take 1/2 of 8. 1/2 of 8 is 4. So now we're at 3, 4, which would be here. And if we wanted to do one more, we could also do 4. And right here, if we do 2 to the 4th power, that's 2 times 2 times 2 times 2, and that's 16. And then half of 16 is 8. So we're going to go to 4, 8 on our coordinate plane, and there's that point. And again, we can graph the line, or the curve, excuse me, that goes through each and every one of these points. And that is another example of exponential growth.